In this example, we're looking at a mechanism which is made up of three links, OA, AB, and BD. OA is pinned to ground at O, BD is pinned to ground at D, and link AB serves as a coupler between links OA and BD. We're given that link OA has a constant angular speed of 3 radians per second, with OA rotating in a counterclockwise sense. And based on that, what we want to do is for the position when theta is 36.87 degrees, we want to find the angular acceleration of links AB and BD. So what we've seen on mechanisms in the past is that although the question may just ask for accelerations, we know right up front we have to do velocity first, because the acceleration equations involve the omegas for the links. So we have to have that done before we can find the angular accelerations. Also, what we've seen for each stage of that analysis, whether that stage be velocity or acceleration, we need to write down a corresponding kinematics equation for each link in the mechanism. So here we have three. So we're basically going to be looking at three velocity equations and three acceleration equations. So let's get going on that. Let's do the velocity first. I'm going to use x and y like this, x to the right and y up. I'm going to start out with link OA, where we know the most information, and I'm going to say the velocity of A is equal to velocity of O plus the omega OA, which we know, crossed with the position vector, which extends from O to A. O is a pin to ground. Omega OA, again, we know that both in magnitude and sense. It's definitely about K. And the vector going from O to A is an Li. So we know that K cross I is a J, so this is an L, omega OA J. So then for link BD, I'm going to jump over to that one and say velocity of B is equal to velocity of D plus omega BD crossed with the vector which extends from D to B. Again, D here is a pin to ground, so that's a 0. Omega BD we don't know. We don't know its magnitude or sense, so I'm going to assume plus, cross that with a vector from D to B, so that's going to be a minus L sine theta in the x, and in the j it's going to be a minus Lj. So when I cross these through, I get an L omega BD in the I. I get a minus L omega BD sine theta in the j. Okay, so that takes care of links OA and BD. Now we want to link together those two links with our coupler here of AB and say that the velocity of A is equal to velocity of B plus angular velocity of AB crossed with the vector which extends from B to A. So for velocity of A, we have an L omega OAJ. That's coming from our kinematics for link OA. Velocity of B we have as L omega BD I minus L omega BD sine theta in the J. And then omega AB, we don't know that, so we're going to assume it's plus, just for the sake of writing this down and let the math tell us whether we're right or wrong. And then the vector going from B to A is an Lj. K cross J, that's a minus I, so this is a minus L omega AB I. Okay, so here we have, with our three lengths, what we've got is what we did is we took VA and put that into there. We have our expression for VB, which we put into there. And along with that third kinematics equation, we have one vector equation, which are really, when we break it into I and J components, we've got two equations, which we will hopefully be able to get everything we need to solve for omega AB and BD. So, the I components, nothing on the left-hand side. We have L omega BD. We have a minus L omega AB like this. The J components. The J components tell you we have the known omega OA times L. On the right-hand side, we have minus L omega BD times sine theta. So it's the second equation that gives us the first answer, which says that omega BD is equal to, the L's cancel out, and get a minus omega OA divided by sine theta. The negative sign, it just means that my original guess up here when I wrote down this equation here, I guessed plus, I was wrong, it's a minus, so it's in the clockwise sense. So then this first equation then therefore gives us that omega AB is equal to omega BD. So we now know that and that. So we're halfway done. We need to do the same thing that we did for acceleration. For link OA, we'll say acceleration of A is equal to acceleration of O plus alpha OA cross with the vector which goes from O to A minus omega OA squared RA with respect to O. O is still that pin to ground, so that's a 0. It says omega OA is a constant, so alpha OA is a 0. So what we have here is the known value of omega OA squared times from O to A is just an Li. For link BD. For link BD, I'm going to write acceleration of B is equal acceleration of the pin D plus the angular acceleration of link BD cross with the vector which goes from D to B minus omega BD, we've found that above, squared RB with respect to D. D is a pin to ground, so the acceleration of D is a 0. Alpha BD, don't know what that is. We'll let math take care of both the magnitude and the sign. The vector which goes from D to B, that's going to be minus L sine theta I minus Lj and minus omega BD squared. RB with respect to D, I need to write that one out. So I have again minus L sine theta I minus Lj. Okay, so what I do is I cross through, I group together my terms, I get L alpha BD for an I contribution, I get an L omega BD squared sine theta And for the j components, I get minus L alpha BD times sine theta, and I get a plus L omega BD squared. That's all in terms of j. And then I go to link AB. Acceleration of A is equal to acceleration of B plus alpha AB cross with the vector which goes from B to A minus omega AB squared RA with respect to B. So this becomes AB. Alpha AB, don't know what that is, either in magnitude or sign. So I'll leave it as assume that's a plus. Going from B to A is a plus LJ minus omega AB squared LJ. So this is a minus L alpha ABI. So, same kind of thing that we had for the velocity. We have three vector equations. Got A sub A sub B. And both of those go into these equations here. We need to balance out our coefficients. And so when I equate these, equating here basically means I substitute in A sub A, substitute in A sub B, balance out my coefficients. And so in front of I, what I'm going to get on the left-hand side, it's a minus L omega OA squared. On the right-hand side from AB, I get an L alpha BD plus L omega BD squared sine theta. And then from the last part here, I get it minus L alpha AB from our AB equation for J. Nothing on the left-hand side. On the right-hand side, I have, for AB, I have a minus L alpha BD sine theta plus L omega BD squared from J. And then I have a term here of minus L omega AB squared. Okay, so what I would suggest that we do, we've got these two equations, that you take this equation and solve for alpha BD. Once you know alpha BD, then you can take the first equation and solve for alpha AB. So these two equations result from balancing out I and J components of the vector equation, which arises from taking our three vector equations, one for each link, and putting in the right expressions and balancing out I and J. Long problem. Not too surprising, because we knew right from the beginning there was going to be a lot of work. We had to do both velocity and acceleration. And for each phase of that, we had to write down a kinematics equation for each link. So effectively, we had 6 vector equations we had to write down. 3 velocity and 3 acceleration. And the process is a matter of vector algebra and balancing out terms and solving for your numerical answers in the end.